For my artifact analysis, I'm basing my team on teaching equation. We all know fostering algebra, we need three things: doing and undoing. You can go the backward way, forward way. We need to build the rule to represent function, recognize patterns. That's how our brain works. From the moment we are born, kids do recognize function from observation and all other things. And also abstracting from computation. So I'm going to base myself on basically recognizing function and talk about it a little bit. With recognizing function, we need to ask a couple of questions like, first of all, how do we know something is a function? Without doing all this calculation or going with the rules of it has to be subjective and all that, we do recognize patterns, right? We look how things are related. We ask questions. And we ask ourselves, can we write a rule that we can use for everything? Can we go the forward way? Can we go the backward way? How does this rule that we just find out work? Can we predict what will happen? And also, if we use different numbers, can this rule still be true? So, about the task, it was an exercise that was given to us in class by the teacher, and that was the first exercise we did in this class. So basically, we are given three different garden types. With the garden types are made of square tiles. Then the problem is asking to determine the 100th garden border and finding a rule to determine the number of tiles needed to build any garden. So we just talk about recognizing patterns and coming up with a rule. And since we're talking about fostering algebra, how can from this problem a student learn to come up with a rule, a function, and then recognize pattern? So when I look at this problem, we can see a pattern. You can recognize a pattern. Garden 1 has 8 tiles. Garden 2 has 12 tiles. Garden 3 has 16 tiles. While being a math student that I am, it's easy to understand that the number of tiles is increasing. So from observation, right? Observation. Math is also building observation. Since we born, kids are built to, the brain are built to recognize patterns. So when you see that the number of tiles is increasing by 4, you want to come up with a rule. So let's see if we can come up with a rule from this. So we go the forward way, because with fostering algebraic thinking, we do and undo. So we can go the forward way, or we can go the backward way. So let's go the forward way. So math is a two-way road. As I say, we can go the forward and backward way. So let's say we have a garden 0, initial garden, starting point. So for the garden 0, it's not given to us, but since we have 1, 2, 3, we can come up with an initial point, right? So the number of square tiles will be 4, because we just said that the first garden is 8 and every time is increased by 4. So if we go backward, we will see that the garden 0 has 4 tiles, square tiles. So basically we came up with a formula, right? Abstracting from computation gives us that we have 4x plus 4, with x being what? The garden number, right? And then from there, you can come out with, this is a formula, and then we can come out with the fact that from plugging the 100th garden number from that formula, we can come up that the border we have 404 square tiles. Well, that's one approach. Someone else can go with finding the area, which is an approach that I don't really like, but also it involves observation. It involves abstracting from computation. When you observe the inside square and outside square, and you decide to find the area of the whole thing, the outside square minus the area of the inside square of each garden, while the only downside will be finding the length or the number of square tiles or each side of the outside of the square, inside square. But after observing the picture of the garden, you can find that the length is only the number of garden plus 2, right? From observation. The emphasis is on observation. So with the length of the inside garden being only n, and then somebody can say, okay, let's go find the perimeter. You have the length of the outside garden, which is the outside square, which is n plus 2, and then the length of the inside square, which is n. Then you can find the formula, right? For the perimeter is n plus 2 square minus n square. And then for the nth guardian, the number of square tiles will be what? 100 plus 2 square minus 100 square. And then we come out with 404. That's a different approach. But what this problem is basically teaching us, it's like mathematics is a science of observation. You can come with the solution pretty easily. Like you can ask yourself, if I could start at the end, like we did, we went back to garden 0 and work our way up to the top. Can we find the formula? Can we find the pattern? Can we find the rule? Can we reverse the process? Then by doing that, can we recognize any pattern? Can we go back all the way to garden 0 as I did and find the y-intercept? Because when I went back to y0, if you make a table and you have, for let's say, x and y, x the number, the garden number, and y the number of tiles, if you go all the way to garden 0, then you get 4, the number of square tiles. That's a y-intercept. And then we see that from garden 0, garden 1, garden 2, garden 3, garden 4, the slope is only 1. That sounds easy. So we do less algebraic computation and more of the thinking. This is the importance of fostering algebraic thinking. We have specific questions that need to be asked, such as, could we recognize a pattern? Can we come up with a rule to solve our section? Like basically, can the rule be applied to everything? We tried it and it worked for garden 0 all the way to garden 100. And we can go to 1 million gardens, it's still gonna work. We did the problem forwardly, we did it backwardly. Pretty much we apply the rules of fostering algebraic thinking. So we stayed away from hardcore algebra and think about reasoning. So a student basically came out with a rule. That rule is a function. That's how you can learn to make up the function. This is the habit of the mind that students could learn from this exercise. We've been doing computation since we know mathematics. Need to work on abstracting from computation and start applying the 3 thinking habits to foster algebraic thinking: doing and doing, building a rule, and abstracting from computation. This is the purpose for this product task. Then we have the arithmetic extension. This is one of the problems we did during week 6. It's taken from the score book, page 112. This problem also basically was asking to find a rule, an equation, which is also one of the principles of algebraic thinking. So when one look at this problem, they can decide to come up with a system of equation with 4 unknowns and 4 equations. Well, that's not staying away from computation. And since we're learning about function and equations, and then we really want to apply the habit of the mind, doing and undoing, coming up with a rule by recognizing patterns, and abstract from computation. We don't want to fall into the hardcore computation anymore. So, as I said before, a student will say, okay, we can get the corners, 2 quarters. We subtract out 6. And another two corner, we subtract out the 12. And then the difference is 12. And then we can have 7 minus x, the unknown, minus 12. And another equation can be minus 5 minus x. I mean, we're going to turn around. We're going to find ourselves in circle with this approach. Student can go in circle with 4 equations and 4 unknowns. That's not applying the habit of the mind. So with a student studying equation and function, they also have to learn that math is not an arcane collection of rules and formulas, but a field whose results are the product of logical reasoning, apply basic statement, and I will add and problem situation. This is a quote from Discourse, page 106. Math is not an arcane collection. It's not a static science. Math involves creativity. So with equation and functions, we don't always have to solve them with system of equation. Like in this problem, we can go with matrices. Matrices is the way to solve this equation. And with matrices, we can also recognize a rule. Make up a matrix A with a diagonal of 1, 1, 1. A matrix B with the value that we have there, 19, 7, 13, 25. And another matrix X, Y, W, X, Y, Z. And then you can find a solution with the going the forward or backward solving using AX equal B, X equal the inverse of A times B. So finding the matrix X, that's going to give us the solution. This problem emphasizes the importance of fostering algebraic thinking. Functions or equations are one way that we connect things as well. Also, because the solution for this problem was not easy to come up, we somehow were forced to think about other ways to come up with a solution, basically. Could think of it differently by asking right questions such as, how things could relate? Does the rule that we could come up with be useful for a general case? How things gonna work? So for this problem, it just shows that coming up with a rule for an equation sometimes involve using other methods like matrices. So let's look at this third one, the factoring task. It's a task that we did in week 9 in class. The habit of mind, as I'm saying, involves doing and undoing, coming up with a rule, with recognizing pattern, observation, and abstracting from computation. Well, with this problem, it's asking to find the factor, solution, x-intercept, y-intercept, the function, like the formula, and find the original polynomial from the graph and the tables. They gave us the graph and the table with values. So we have to use our brain, observe. Well, one can decide just to go with the formula of a second degree equation, ax squared plus bx plus c. I mean, in this case, the a is equal to 1, but that's not the way to go, to do things in a complicated way. We are so reluctant. At any level, students are so reluctant to plug in any valid x and y values to find an equation of a function. Even if it's given, we are so reluctant. We always want to go the hardest way. Well, fostering algebraic thinking involves staying away from hardcore computation. So let's go with observation with this one. And abstracting from computation. How are we going to come up with a rule? Well, we are given the factors, right? We have the values of x. We can look at the graph. Look, first two values that we can get from the graph are the zeros, right? The x-intercept. That's easy. Well, plug it from the formula. A times x minus x1 times x minus x2 equal y. from there, we can get our formula. So it does not really matter which form we write the second degree equation. All it takes is plugging in the given point, the given information. It's the same. We can apply this rule when teaching function to any kind of equation. Let's look at a linear function, for example. The linear function is in form of the equation of a line. I mean, y equal mx plus b with m be the slope. For example, if we are given a point like 2 and 1, and the slope m equal 1/2, for example. It's so hard for students to just, okay, I have this information, I know how the equation of a line should look like, to just plug this information. I mean, it would be easy. Just do 1 equal 1/2 times 2 plus b. But many students won't do that because we are not taught that way. Many students will go with the hardest way, using the information with the point slope equation, like come up with a formula like y minus 1 equal 1/2 times x minus 2. So we end up manipulating that equation around until we get the form of y equal mx plus b. Why not just use the information given? Because we already have an x and y and a slope. Why not use the information given? I mean, fostering algebraic thinking also implies abstracting from computation. With teaching equations, students, of course, they recognize patterns, but also they need to abstract from computation. They see how things are related. Can we just take the information given and plug it into the function? So fostering algebraic thinking has to push students to stop being reluctant to use the point given or the information given to solve an equation. Algebra is not taught the way it should be taught. Could you imagine if students were taught that a valid x and y, who will plug into any type of equation to find the function? That could make things super well easier. Then help students abstract from computation to foster algebraic thinking. When talking about abstracting from computation, the age problem, which we're gonna see right now, taken from the Discord, page 32 to 34 from our book, it was one of the assigned problem in class as well, is one of those that help us to really further see how we can take a problem that when you look at that, you think about doing all this calculation, can be abstracted from computation. I have studied modulo in maths when you have to calculate the remainder, though, but I didn't really want to think about this problem that way. Students shouldn't be thinking about that, doing modulo, the remainder, or applying those formula. In order to foster algebraic thinking, they have to look at the pattern, ask themselves questions. Like, for example, for a number to be divisible by 5, it should be a multiple of 5, right? So if the number is x, a multiple of 5, for it to have a remainder of 3, we should add 3 to a x, right? So thinking of that pattern, we could abstract from computation and come up with a general rule or a function. We also gonna look at how things are related here. To go with this problem, a student can decide to go with making a table. One side is the number, the other one is a remainder, right? You put 8, remainder 3, that's 5 plus 3. 8 plus 5 is 13. 13 plus 5 is 18. 18 plus 5 is 23. So the remainder is still constant, still 3. And then going back to the idea of what we saw in the board and tax problem, we can think of, okay, from 8 to 13 is 5, 5, 5. So the slope is 5, right? Yeah. So you know the equation, the linear equation of from y equal mx plus b? We have our constant that's 3, and then we have a 5 as a slope. So we come up with y equal 5x plus 3. We can apply the rule for when the number is divisible by 3 with a remainder of 1, right? We apply the same thing. One side we put the numbers, the other side of the table we put a reminder. We put 4. 4 is divisible by 3 with a remainder of 1. So 4 plus 2 is 7, 7 plus 2 is 10, 10 plus so and so. So the slope there is 3, and the remainder is 1, and we come with a general rule of 3x plus 1. We could ask ourselves, okay, if we start at the end and work our way up to the top, basically do the backward, the reverse order. This is also one of the ways algebraic thing, like the habit of mind, is used to come up with a rule, right? Then by doing that, we recognize a pattern, right? So if we get, like for the formula 5x plus 3, we find the function. The y-intercept is 3, and the slope is 5. Do you see how things are related? How from an exercise that's asking some, like the reminder, how the number are divisible, you can go the other way. You could go with hardcore computation, coming up with modular reminders. You're basically coming with an equation, a linear equation of a line with an intercept equal y-intercept of 3 and a slope of 5. Wow. So, and then we don't really care about being right or wrong. That's something we need to know. Math is not about being right or wrong. It's not, I mean, school mathematics want to teach us that it's a science of good grade, being right or wrong. Math is a science of creativity. Like Driscoll says in page 29, we should ask ourselves why a particular computational algorithm work, as well as when they work. So if the reasoning is correct, then it should be correct somewhere. So that's how, with recognizing the pattern, we ask ourselves the question, can this rule be applied to everything, to different numbers? Yes, because we can get the formula with divisible by 3 with a remainder of 1 from the process that we came out with divisible by 5 with a remainder of 3. For the second part of the H problem, they can also look at the pattern. They don't have to come out with setting up a system of equation. Like, ask yourself this question. If a number is divisible by 3 and have a remainder of 2, and the same number is divisible by 5 and have a remainder of 2 as well, that should raise one's curiosity, right? The same number, let's call it x, should be divisible by 2 and 5, right? Plus a remainder of 2. So could we predict what's gonna happen here? Yeah. So the number is divisible by 2 and 5 should be a multiple of 15. Then adding plus 2, the remainder, we came out with the number is 17. I mean, we can make also the table, go down the list, adding 15 to the 17, we got 32, 47, etc. Right? So we have a list, the number, the remainder. We have 17, 32, 47, and the remainder will be what? 2. So we came out with a model, a rule, a pattern that the numbers divisible by 3 and remainder of 2 and divisible by 5 and remainder of 2, y should be 15x plus 2. But wait, that was not the end. The same number should also be divisible by 7 and have a remainder of 5. Well, since we already know the process in mind, we already have the process in mind after observation, a student can say, well, we knew that the number should be divisible by 3, 5, 7. So the number x, the h, should also be divisible by 15 and 7, logically. So coming up with a model or seeing how things are relating, we assume that the h should also be a multiple of 15 and 7 plus a remainder. So x will be a form of what? Multiple of 15 and 7 is 15 times 75, 105. So it's going to be 105x plus remainder. Come on. We're coming out with a rule from abstracting from computation, with observation, with asking questions. We are basically staying away from this hardcore computational algebra. Boyer on page 12 says, the brain activity was greater following mistakes for individuals with a growth mindset than for individuals with a fixed mindset. We're going to make mistakes in the way. It's not about being correct here, but the problem is that what do we gain from that? The growth mindset, instead of being fixated with one way of doing things. So why not make mistake? So with learning functions, students also can make mistake. That's how we grow our mind. We know the remainder should be after we divide by 15 and 7. So after process of observation and pattern, we come up with the number divisible by 15 and as a remainder 2, divisible by 7 as a remainder 5. What the function given is y equal 105x plus 47. If we choose different number, is still the model, the rule we came up with gonna be true? Let's try x equals 0. We find out the age is 47. 47 divisible by 3, the remainder of 2, divisible by 5, the remainder of 2, divisible by 7, and the remainder is 5. We could go down the list with x equal 1, 2, 3. The model is still gonna be true. Even if we reverse the process and start at the end and work backward, it's still gonna work. So that makes sense. So through this process, students really did the doing and doing observation, apply the 3 habit of the mind, learning about equations and functions. So this is an interesting thing about solving this problem, staying away from hardcore computation. In fact, another exercise that could help us when teaching function and equation is the high school algebra problem. This one was taken from Driscoll, page 68. Basically, the problem involves the concept of comparison of system of equation. The challenge here is using more of algebraic thinking without falling into the trap of doing hardcore algebra. Well, we want to stay away from doing hardcore algebra. Well, when students see equation, we talk about equation, recognizing pattern and stuff, but the way equation is taught is we see numbers. So we just jump into hardcore algebra. This is what school mathematics taught us. We don't really think of equation, we do equation. So for this problem, we don't want to teach students how to do equation. We want to foster algebraic thinking. So the challenge is to have students calculating without calculating more habitual. But how can we stay from the hardcore computational? We all know that we all natural mathematics user, right? Boller on page 65. Say we all natural mathematics users. So we are born, since we are born, we love mathematics. Since we are baby, infant, we do recognize patterns and line. So I decided to ask myself question. Go with question. When in doubt, question all the time. The first question was like, can I obtain other equation from a linear combination of other one? Yes, of course. And the way of doing it, the easy way, is to use matrices and determinants. As we said previously with the arithmetical extensions problem, math is not a static science, it's multidimensional process. We can use different way to get to the point. We don't have to use system of equation all the time. So we want to come up with an underlying structure for this problem. If we look at that, we can observe that the pair of equations have the same x value determinant and the same y values determinant. So we can get the commonalities between these equations. If also we observe the linear combination or pattern between this pair of equations, we can find the commonalities, but that's not obvious to the human eye. We actually have to do the calculation. That's why using determinants is the way to go. We could ask ourselves a question. If all these equations go to the same point, any pair of them will have the same solution. Well, do all these equations go to the same point? Yes, they do. When x equal -1 and y equal 2, they go to the same point. So they must have something in common, the same solution, right? So we use hardcore algebra, yes, to find the point, and when we're calculating the determinant, but that's not the point, because looking at the commonalities and why involve using determinants. That was simpler than going with the hardcore algebra. So being open-minded in math it's a good approach to any problem. We can go many ways, but which one is gonna foster our algebraic thinking? Because we could have just sat there and start calculating, comparing each of them, multiplying the second pair of equation by 7, we obtain 14x plus 21, y equals 28, and 35x plus 42y equals 49. When we multiply the first equation by 6, we have 6x plus 12y equal 12, and 24x plus 30y equal 36. By doing 14x plus 21, y equal 28, minus 6x plus 12y equal 12, and 35x plus 42y equal 49, minus 24x plus 30y equal 36, then we obtain 8x plus 9y equal 10, and 11x plus 12y equal 13. This is the third equation. We could have gone that way, comparing each equation, but this is not obvious to the human eye. It's not. That's why using matrices and determinants, and using the fact that if they go to the same point, then they should have the same solution. Function, equation, students should get the habit of observation, coming up with rule, open-minded, using other options. This is what high school algebra could teach us. When teaching, we also have to have students see any sort of representation of equation or function. That's why we have diagraphs. A diagraph is a different way to represent a function, because functions are represented a different way. Let's look at these 7 different types of diagraphs, right? We have this link here. Let's look at what is a diagraph first? A diagraph is a different way to represent functions. So students can explore the relationship between input and output by manipulating interactive double numbers line, with the green dot being the input and the dark black one with the output. So students can learn how to find equation, how to justify the pattern. All right. Let's look at the possible solution. We have this diagraph. When I move the green dot, both of them move from the positive and negative side. We see that they are parallel to each other. The value of x equals the value of y. It's aligned with the equation of y equals x, right? Let's look at the second one, with the green dot being the input and the black the output. When we move the green dot, we see that the value of y, the black dot, is the value of x plus 2. Is the value of the input plus 2. Like if the green dot is 4, the black dot is 6. So it's aligned with the equation of y equals x plus 2. Right? You can observe it. The third one, when the green dot, let's call it x, and the black one y, moves, the green moves, the value of the black dot is twice the value of the green dot. So the value of y is twice the value of x. We have the line y equal to x. Let's look at 4, diagram 4. When x, the green dot, moves, the value of the black dot y is half the value of the green dot. In other words, the value of the output y is half the value of x. So we have the equation of the line y equals x over 2. For diagram 5, we observe that when the green dot is moving, the black dot is moving at the same rate, symmetrically in the opposite direction. That means the value of x is equal to the opposite of value of y. This is the equation of y equal minus x. Diagram 6, when the green dot moves toward the positive direction, the black dot moves at the same rate and direction as well. It's like diagraph 1 with the equation y equal x. But when the green dot moves toward the negative direction, like in diagraph 5, so the equation is y equal negative x, right? This type of function is absolute value of x, right? You can see that. If the input is negative, the output is still positive. If the output is the input is positive, the output is still positive. For 7, we see that when the green dot, the input x, moves, the black dot output moves, landing in the value that is equal to the square of the value of x. So, well, this is a parabola, y equals x squared. So this activity, as we see, help foster algebraic thinking by helping students look at the structure and image of what they have been doing, studying. You'll be studying equation function. Now you can look at the structure and the big image, big picture. Students can think about how the input and output of different type of graph that they are not used to do interact, how they look like, how they are related to each other. By doing this activity, students should be asking themselves, what is happening? What is staying the same? What is changing? Is there a rule that they could use to represent? So, for example, when looking at the diagraph of the absolute value y equal absolute value of x, it's not enough to say that they got an absolute value graph. Students need to be paying attention to structure as well. So students are pushed to look at the pattern when doing this activity. When they are moving the dot for the input, the green dot, and the output, if the input are increasing or going to the negative side or positive side, students could be asking what will happen to the output. Also, when they look at the positive side, will it give them something positive or negative? Then when students try to the negative side of the graph, what would they get? So depending on the equation that they come up with, the student have to decide whether to use the absolute value or not. So the idea of moving past the 0 into the positive and the negative is what makes students see whether the graph might be an absolute value or not. This is how students could come up with the equation of y equal absolute value of x. And by studying absolute value like this, they will never forget it. Through this activity, students can observe also the rate of change, which is a way to visualize the slope. Visualizing the slope is how students normally doing graphic on the Cartesian coordinate system. However, by abstracting from computation, students, instead of looking at the static graph and asking themselves if the slope is changing, students have the opportunity to observe in real life time how the rate of change is happening. This is one of those things that students could learn from this activity that they can't necessarily learn from the Cartesian coordinate system. So diagraph are different type of mathematical representation of equation, which helps students think of input and output and how they relate to each other. They are not used frequently though. And I think they should be used frequently. They were recently invented, maybe that's why. Because I think diagraph could help students represent equation with much more than a x and y graph coordinate. They actually see, they feel comfortable because they actually come up with a rule and they got to see how the structure, how things are related. So I think with diagraph student, we have another perspective of equations. So another way student can also visualize function or equation is through graphing them to an XY coordinate graph. One of the tools that can help student graph is called GeoGebra, where they can actually put the values and see in real time how the rate of change changes. It's a way of really visualizing the function, because after observing the pattern, after coming up with an equation, after coming up with a rule, we need to graph. Dynagraph, they do it, but XY coordinate graph is also necessary. So we're gonna go through this link and see. So we are here on the GeoGebra graphing calculator. We can try to graph the equation of absolute value. We talk about absolute value when we did the dynagraph. We say that the value of the output is still positive, even if the input is negative. We see that even though we have a negative 30x, we can zoom out, see that clearly. Negative 80x, the y is still positive. 80x, the y is still positive. So even though the value of the input is negative, the output is still positive. And then through this one, we can actually observe the rate of change or the shift. Let's say we try to graph y equal absolute value of x minus 1. I'll zoom in to see the difference. Yep. There we go. We can actually see the shift visualizing. That's actually how students can see actually what they're studying. They can actually visualize it through this technology tool, GeoGebra graphing calculator. They see the shift. We have the graph of y equal absolute value of x and y equal absolute of x minus 1. The same way if we try to graph y equal absolute value of x plus 1. We see the shift as well. Now it shifts up. So we observe the changes in the graph, in the function. So it's good to study function. It's good to memorize values, but fostering algebraic thinking doesn't depend on that. Fostering algebraic thinking depends on observation. Why value of x plus 1, the graph is up? We can actually see that in the graph. X doesn't change. It just goes up 1. The graph is the same, but it just moves up. We are actually visualizing it. That's why I think when teaching about equation and function, every teacher should also have a way of having students visualize actually what they're learning. This concludes my presentation of fostering algebraic thinking with teaching equation and functions. I do believe that applying the habit of mind, having the habit of mind of doing and undoing, extracting from computation, coming out with a rule, observing pattern, actually is a way of fostering algebraic thinking, and every teacher teaching equation function should have that in mind. Thank you. This was Merveille Madina.